This YouTube is about elastic potential energy or spring energy, and I will often refer to this in class as EPE. So let's consider an unstretched spring held horizontally, and let's say I put my hand on the end of the spring and I pull outward to stretch the spring, and so the delta X is to the right and my force of my hand on the spring is to the right. And so the work done by my hand on the spring is going to be bigger than 0, since both of these forces are, both of these vectors, I should say, delta x and f of h on s are parallel to each other. And on the other hand, let's say I put my hand on the spring and I compress the spring. A displacement delta x to the left, but my force of my hand on the spring is also to the left, and so again the work done by the hand on the spring is bigger than 0. So the work that I will do on the spring is positive whether I stretch the spring, that's this middle picture, or whether I compress the spring. And so in order to get a handle on what this work is, let's draw a force versus stretch for the spring. And so this would be the force that my hand exerts on a spring when it gets stretched. And so it's going to be a straight line, and if you just consider a little bar underneath the straight line, this little bar is going to represent the area under this little bar is going to be given by F delta X. So that would be the force. So I'll say F1 times whatever the distance that the tiny little distance that I displace it here, and so the this F1 times this small little displacement is going to represent the area of this bar, and if I sum all of those bars all the way from here to here to here to here to here, it's going to represent the area underneath this curve and this straight line, and that is going to represent the work done, because each one of these bars represents the work done for a small displacement. So in those terms we know what to do, because this area here is the area of a triangle. The area of a triangle, this is a particularly simple triangle. A right triangle is simply 1/2 the base times the height, and so 1/2 times the total amount stretched times the maximum f, and so this f right here is f times delta x. So let me erase this and then redraw this up here. It makes a little bit more sense. 1/2 times the maximum stretch times k delta x, and so this would be the max force right here. It's going to be basically 1/2 times k times delta x squared. And in a similar spirit to what we did for gravitational potential energy, my hand, if it stretches the spring or compresses the spring is adding energy to the spring system. Positive work is being done by my hand in either case, and so we're going to conceptualize that and bookkeep it by defining elastic potential energy as 1/2 times the spring constant, k is the spring constant, times, instead of writing delta x, we'll just assume and understand that x means the amount by which the spring is compressed or stretched, x squared. And so in the next YouTube we'll do some examples, but this is the basic idea. And so now so far we've talked about kinetic energy, the energy of motion, gravitational potential energy, which is the energy of being in a gravitational field, and then elastic potential energy, which is the energy stored in a spring system.